I'm Roberto Iacoviello from RAI R&D. RAI is the Italian public broadcaster, and this is the report on the activities of the MPI Enhanced Video Coding Evidence Project. Next slide, please. So in video internet traffic has exploded in recent years, and this growth has placed burden on internet infrastructure, leading to network congestion, slower download speeds, and higher cost for both consumers and service provider. One solution, of course, is video compression. And mainstream video coding standards are working on that, and all of them are exploring deep learning. And that's because deep learning-based coding tools have attracted attention in recent years, because they bring significant improvement in terms of the compression performance and also on the reconstruction quality. And a standardization of deep learning based coding tools, of course, is needed. Leonardo, don't you have another slide before this one? That was the introduction slides.
Oh,
just this one. Oh, yes, you have MPI EVC Evidence Project, the previous one.
Yeah, oh, okay, so it jumped it twice.
Yeah, exactly. Okay, so as I said, this is the, standardization of deep learning-based coding tool is needed, and that what is MPI is trying to do. In particular, MPI Enhanced Video Coding mission is to exploit advances in deep learning to develop video coding standards that improve the coding efficiency. Next slide, please. Our starting point is the MPEG-5 EVC, the essential video coding from MPEG. In particular, we are using an open source provided by Samsung. This standard was deployed in 2020 as an alternative of, to AV1 from Alliance for Open Media. And it has two profiles: the baseline profile that is royalty-free because it's made with technologies older than 20 years, and a main profile. Moreover, it supports 8 and 10 bits video coding with resolution up to 8K. And it also includes features such as support for high dynamic range and wide color gamut. In its baseline profile, the bitrate saving is almost equal to HEVC, while in the main profile, the bitrate gain over HEVC is 36%, at least for 4K resolution HDR sequences. So the main idea of MPI EVC is to boost EVC with deep learning tools. And next slide, please. Yeah, and this is the typical traditional framework for video coding that shows the generic parts of a video encoder. So the main idea is to reduce information in the picture by exploiting redundancies in the picture, and this can be achieved usually by two modes. Predicting parts of the picture from neighboring data within the same picture, and this is called intra prediction, or from data previously decoded in the previously decoded picture, and this is called interprediction. Interprediction exploits the temporal dimension. To reduce the data, a residual signal is created based on the predicting samples, and this residual signal is transformed, usually with discrete cosine transform, and then quantized. The resulting data is entropy coded. That is the lossless part of the pipeline. As you can see in the Azure box, that shows the decoder part inside the encoder, the quantized data is further reconstructed through a dequantization and inverse transformation step. By adding the predicted residuals, the input data is then reconstructed. To further improve the visual quality, filters such as the blocking filter or sample adaptive offset are used. Finally, the reconstructed picture is stored in a picture buffer. Now, mainstream video coding standards have adopted in the years very complicated coding unit partitioning, for example, quad tree with binary and ternary tree. Moreover, they are double the number of angular intra-prediction in order to capture the edge direction more efficiently. They are using cross-component prediction, or they are using affine motion compensation in order to cope with the non-translational motion. I mean, they are all of them are handcrafted algorithms that rely on human expert to design and engineer a feature that then they are using into the codec. In MPyVC, we decide to take a different approach by leveraging deep learning. MPy, however, MPyVC has already developed the use case and functional requirement, and it's getting ready for the call for technology. But before this step, we decide to run the MPyVC evidence project with the goal to improve the EVC codec by 25% in coding gain. And the effort is focused on the hybrid approach. That means deep learning-based algorithm combined with the traditional video codec. And up to this point, 4 tools have been investigated by the EVC project that you can see in the red rectangles, namely intra and inter prediction enhancement, super resolution, and in-loop filter. Next slide, please. Intra-frame prediction removes the spatial correlation within the same picture, as we said, generating a predictor for the block to be coded by exploiting pixel values from decoded neighborhood that we call context. Then the this predicted block is then subtracted from the original block, producing a residual that then is transformed, quantized, and entropy coded. And the rationale behind the interprediction is that encoding the difference between the block to be coded and the predictor require fewer bits than encoding the original block. I mean, the better the predictor, the lower the energy of the residuals. That means the higher the coding efficiency. And we addressed this challenge of predicting a block, given its context, as an image in painting problem. That means recovering pixel from an image that are unavailable due to any reasons. Mask convolutional neural networks have been recently proposed for imaging painting, exploiting the a priori information from the context to recover the missing pixels. And the method that we propose relies, as I said, on the mask convolutions to generate a predictor starting from a decoded context that in our case is 64 by 64 pixel, and the context is sent to the autoencoder. Then the autoencoder returns a predictor that we and we replaced the EVC predictor mode 0, that is the DC mode predictor. We replaced the DC predictor unconditionally, so we don't need additional signaling to the decoder, and in this case, the bit stream is decodable. Next slide, please. So this is our reference schema, and the mask autoencoder is trained in a supervised manner, extracting random patches from about 800 pictures that are representing various type of contents. The training lasts 1,000 epochs, and the autoencoder is trained to minimize the absolute error. And next slide, please. And so we tested on QPs range from 22 to 42, and we replaced the coding unit from sites 32 to sites 4. And our encoding experiments with JVET class sequences that are commonly used for similar tests have shown results of 6.55% on QP range 2247 and 6.89% of the extended QP range 2242. So feature challenge will include modeling the encoding rate in the loss function, and also controlling the complexity of the convolutional autoencoder so that it can be implemented in hardware, for example, in FPGA. Next slide, please. So super resolution creates a picture with 2 or more times the linear resolution. That means the output picture has twice the width and twice the height of the original picture. And our starting point is this paper, Densely Residual Laplacian Super Resolution, and we choose this one because it introduces new type of architecture based on cascading over residual which can assist in the training of this neural network, and also because of this feature called Laplacian pyramid attention that weights the feature according to their relative importance. The super resolution network is added as a post-processing tool. That means the picture before encoding with the EVC baseline profile is downscaled, and then the super resolution network is applied decoder side to get native resolution. Next slide, please. So we combine these two tools, that means intra and super resolution, in the same EVC codec. We perform a kind of ablation study. So that means that on the right of this picture, we used the pre-train super resolution network as it appears in the original work of its authors. And on the left side, we fine-tuned this super resolution network on the MPI reference training dataset, because we have also built a training set for the neural networks. And the results of this activity then have been compared to the classical bicubic interpolation algorithm used as a baseline that you can see in the middle in this picture. Next slide, please. Yeah, so these are our results. As you can see from the table on the left, with the pre-trained network, the BD rate gain is 4.53%, while our result after the fine-tuning is 16.57%. And till now, this is our best result. Next slide, please. So for the future, these are the tests that we have planned. I mean, test the fine-tune super resolution network versus the training from scratch. I mean, the network was first pre-training on a large data set by the author of the paper, and then we fine-tune on our data set to improve its performance on the specific super resolution task. Then the other test is to test random patches versus important sampling. I mean, it's common to train super resolution network using a patch-based approach, where small crops of the input picture are used to train the super resolution network. The goal of this approach is to reduce the memory requirement of the model and also to allow for more efficient training. But when it comes to extracting these patches, there are two main modes. I mean, one is random sampling, and the other one is the importance sampling. I mean, random sampling involves selecting patches randomly from the input image without any strategy. On the other hand, important samplings involve computing a metric that measures the importance of each patch inside the picture. And this approach, of course, is more complex, but it can lead to better performance since it can select patches that are more representative of the whole picture. And in the last test, we would like to compare the patch-based approach with the full-frame training. I mean, full-frame training involves training the super resolution network on the entire input image without dividing into patches. This approach, of course, is more computationally expensive than patch-based training, since it requires more memory and processing power. However, it can potentially lead to better performances since the network can learn more global feature of the picture. Next slide, please.
Roberto, you are left with 2 minutes.
Oh, okay, thank you. So the other one is the in-loop filter. Our starting point is a deep learning approach for multi-frame in-loop filter of HEVC. We have performed the image extraction before the EVC filtering, and to improve the quality of extracted images, a neural network is used for this image enhancement. And I mean, partition information is retrieved from the EVC process, and this because this information is needed for the neural network, because each part of the picture can be optimized based on its characteristics. And the output of this process is an improved image which is ready to be integrated into the EVC pipeline. And finally, we are in the BD rate calculation is currently in progress. Next is interprediction. Interprediction starting point is the affine transformation based deep frame prediction. We have tested the software, and this means that we can now proceed to the next step, which is to integrate the software with the EVC project. And as you probably know, the integration process involves several steps, including the porting of the software from the HEVC implementation to the EVC project. And last slide, please. Future plans and perspective. As a future plans, we would like to combine, also the in-loop enhancement with inter-enhancement and super resolution. We have just started the work on interprediction, try to integrate the software into EVC. And then we look forward to completing the integration of the deep learning based tools into the EVC project. And finally, my last message is that I think it's the right moment to join EVC, because we are in the collaborative phase before the call for technologies. So we are sharing knowledge, expertise, and provide support as needed.